Hello, this talk is about smart contract security and GLOW. I'm Sam Bown. I teach at City College San Francisco, and with my corporation InfoSec Decoded, I do consulting and training for corporations, and I presented at DEF CON and Black Hat and HOPE and a lot of other conferences, including this one. Everything I'm showing you is free open source software, and all the instructions for the projects and lectures and videos and everything are all available for everybody for free on my website, samsclass.info. And what I'm showing you today is in this cryptography course I teach. And so here's the concepts that you need to understand what we're going to talk about here. A blockchain is just a distributed database where many servers have identical copies of the database, and it is designed to make it easy for people to verify that that database is intact and has not been altered. So it is an effectively immutable record of past transactions where people can agree very easily on what the truth is about what happened. You can add not only financial data, but you can add other kinds of data to the blockchain, and you could even put instructions on how to process that data on the blockchain, so each further block has some kind of calculation done, and those are smart contracts, which are all the rage these days. For example, non-fungible tokens are smart contracts. Solidity is the main language used to write these contracts, and it is, in fact, a really miserable language for the purpose. It's based on JavaScript, and it has a lot of really serious flaws, which has led to a ton of spectacular hacking incidents where people stole vast amounts of money, up to $660 million recently, from blockchain contracts. They are spectacularly insecure in many cases. So there is a movement underway to develop better programming languages, and one of the newer, more advanced languages is GLOW, which I'm planning to show you. So let's start with what a blockchain is. This website, andersbrownworth.com, has a nice live demonstration of a blockchain, which you see here. So a blockchain is just, you have a block number, you have a previous hash and a hash. This is the genesis block, the one that starts it. So you put in some data. Now, whoever mines a block gets a reward. So if Sam mines this block, Sam wins 10 coins. All right, now that that data has been put in there, this block has not been mined. As long as you're adding data, this block is still changing. When it comes time to mine this block, you pick random numbers for this nonce until you get a hash that starts with a lot of zeros. So when you click mine, it will just try a lot of random numbers, and when it wins, it will turn green. This number, 72935, combined with all this data, created a hash that started with 4 zeros. 4 zeros is the difficulty of this blockchain, and a block is only mined when somebody has found a way to make the hash begin with 4 zeros, and the first person that succeeds among the miners wins, like a person that drew a winning lottery ticket. So if Judy mines the next block, Judy wins 10 coins. And maybe there's other things going on, like Sam sends Bill 2 coins. You have things to put in here. And there may be other things like data and instructions because somebody is putting a smart contract on the blockchain. So there will be some kind of instructions and some kind of data, and each future block will execute those instructions and change the data. So you put in all that stuff, and then this block gets mined. And it turns green when it's mined, and then you keep going that way. And if somebody tries to cheat, like Sam tries to say he won 100 coins, not only does this block broken and not mined anymore, but all the future blocks are broken too, because the hash from this block is included in the next block. So if you verify the latest block, you can have high degree of confidence that the entire chain is intact, and that's what a blockchain is. That's the point of it. It's just a way to have a series of commits of transactions being saved in a way that we will never have an argument about them after they're mined. So you can do contracts, and you can store data on the blockchain. And so let's, there. So let's have a demonstration of a smart contract. Here's a smart contract that mints a coin. And I'll just do this one live. There is a great online JavaScript browser. Remix.ethereum.org is an environment that lets you simulate an Ethereum blockchain right in your browser for free and learn how they work. So if you go here, here are some contracts I've got here, and the one I want to look at now is coin.sol, which is here. There's really not much to it at all. There is a address of a minter, and when you initiate the contract, when you create the contract, the minter will be the person who sent the request to deploy and create this contract. They are the person who can then mint coins with this mint function. They can just mint these objects, and then there is a function to send objects to other people. It's just very simple. I'm creating a currency. This is what you do if your initial coin offering that was all the rage a few years ago. So you write the solidity for this, then you compile it. And when it's done, you can go to compilation details. You can see what a contract looks like. It's just written in a form of assembly code. And this assembly code looks like just any other assembly code. Push, call value, is zero, jump, revert, duplicate, pop. Just very common assembly-like instructions. And that's, in fact, compiled down to bytecode, which is just a bunch of hexadecimal instructions that encode that in bytes, and that's what actually goes on the blockchain, just a blob of hexadecimal data. So, to deploy that onto the blockchain, I go here, and there's old stuff there, so I'm going to clean my simulated blockchain by going to Berlin and London again. All right, and now I got a clean simulated blockchain with some accounts that each start with 100 Ether. So I'll work from the first account and deploy that contract. Now that cost me a little bit of money. My account is now 99.999. A tiny amount of money was spent to deploy the contract, and this green check mark here tells me that my transaction was accepted and mined and added to the blockchain. So now there is a contract. The contract has an address, and the contract has some functions like mint and send and so on. So I can now mint some money. When I mint money, I have to tell it what address is going to own that money and how much it's going to be. So I want it to be owned by me, the first address here, so I copy it. And then I come down here and paste in that address. And then for an amount, I'm going to put in 222 times 10 to the 18. In the Ethereum world, you use 10 to the 18 as the smallest unit of money called away. 10 to the 18 of those is an ether. So this is 222 ethers worth of this new coin, which is not equal to ether. It's just a new coin I've minted. So the transaction is successful. And I can now expand the blue-gray balances. Okay, now I can see the balance of any account. So I'll copy this account again and see what my balance is here. And it is 222 times 10 to the 18th. So I have some coins of these new coins I've created. And I could send some of those coins to somebody else. So I'll send some to the second person, go here and copy that account, and then go back to the first person because that's going to be my from address. And so I'm going to send to the receiver, which is that address I just copied, and I will send them 5 times 10 to the 18 coins. So my current balance is 222 times 10 to the 18. I perform this transaction, and now if I call for it's now 217 times 10 to the 18, so I now have depleted my balance by 5 times 10 to the 18 of these coins. And the other person, of course, has the 5. If I copy that address and put it here and call, they've got 5 times 10 to the 18 coins. So that's how it works, just like you'd think it would work. That's minting a coin. Now, let's try and see how fallback functions work. Now, if you have a contract, you provide certain functions, and those functions have certain parameters. But what if somebody calls your contract incorrectly? They call a function that doesn't exist, or they call a function without passing in required data, or they just transfer money to your address without calling any function at all. Well, instead of rejecting those things, what you do in Solidity is you use the fallback function. If you define a fallback function, it will be used to resolve all these conditions. And that might be good, but the problem is you can put code in the fallback function. So think about what this means. If I'm just receiving money from somebody for any reason, when they send me money, I can now execute code inside their contract. Just the ability to receive money grants me code execution permission in other people's code, which is completely insane and dangerous, and as we'll see, has been exploited many times. So here's the reentrancy attack. This is the attack that destroyed the first major contract on the Ethereum blockchain. After years of trumpeting it and getting people to invest, they announced the DAO, the Digital Autonomous Organization. It was supposed to change the world by making the new glorious future of smart contracts, and it was a disaster. The whole thing got hacked within a month. People stole all the money. $50 million were stolen with a reentrancy attack. And the point is, you have a DAO here. There's some ability to get money from the DAO, and with a malicious contract, they were able to call for withdrawal, and when the withdrawal came in, they were able to go to the fallback function and use that to call withdraw again. So when you tried to pay me once, I would trick you into paying me many times, so I could get much more money out than I was supposed to be allowed to get out, because I was able to execute code when receiving money. And so let's see a simple example of this. So here's a contract that is just intended to allow people to withdraw gifts, but only up to a limit. So there's a number called gifts, an integer that says how many gifts people can take, and people can withdraw money. And when they withdraw money, it checks to see if gifts is greater than 0. If so, it sends money to somebody and then decrements the gifts variable. And after gifts hit 0, you can't take any more money. But the problem is, it sends the money first before subtracting from the gifts, and this send can hit a malicious fallback function that calls it again and again and again before it ever gets down to this decrement statement, and that's what we're going to do. So here's the attacker's feedback function. They make another contract that connects to the first one and has a fallback function, and that will just, when it receives money, it will withdraw again up to 10 times. Instead of doing it an infinite number of times, it'll call 10 times withdrawal when it was only supposed to be allowed to call it once. So that's the game, and let's try this one live. So let me go to my blockchain simulation here, and we'll look at fallback.sol. So here's fallback.sol. This is the code. And this one here is a very simple example of a fallback failure. The fallback code is here, and so when it collects money, it also changes the owner. So it takes the money, and then it changes the owner of the contract to this person with this owner equals payable message sender. So let's compile this one. All right, and clean my blockchain. Go to Berlin and back to London, and now I got a nice empty blockchain. And now I deploy this contract, and the green check mark tells me it worked. And so now I can contribute money into this account down here. So that's what I'm going to do. I'm going to contribute 10 ethers from the first account into that function. So right now my balance is 99.9. I contribute. Now it's 89.9. So I put 10 ethers inside there. Now I hit the Get Balance button and the balance button here, and I see that my balance is 10 times 10 to the 18, so the 10 ether went into that contract. And, all right. Now I can see who owns the contract, and the owner is 5B3, and 5B3 is me. I'm the one that paid for this and contributed the money and deployed the contract, and I'm the owner. Now we'll do the attack. I'll select the second account up here that's 100 Ether, and I'm going to contribute 1 Ether this time from that account, but I'm going to use transact. Instead of using the contribute function, I'm going to send a transaction which will send the money to the contract without calling the function, and that will go to the fallback function. Notice the transaction succeeded with a green check mark, but it called the fallback function. And since it called the fallback function, notice who owns this. My new address is ABH, and the owner is now ABH. So now I own the money. Now if I look at the balance with get balance and balance, it's now 11 times 10 to the 18, 10 from the first guy and 1 from the last guy. But anyway, now I own it, so now I can withdraw. Notice right now I have 98 ethers, and the other account has 89 ethers that put 10 ethers in. So my current balance is 98, but I withdraw, and now I have 109 ether. I just stole 10 ether from the first account by changing the owner, and that was with a malicious fallback function. So